In this video, we're going to have a look and see how we handle complex numbers. We always write a complex number as a plus bi, where a and b are real numbers, and I is the square root of -1, or, if you prefer it, I squared equals -1. This gives us a problem straight away. What do we actually mean by plus? It's all very well to think that you know what you mean by plus. If you go for the normal idea of 1 plus 3, you would think of the number line. You would go 1, 2, 3, 4, 5, etc. And then on the number line, you would say 1 plus 3 is just go to 1 and count 3. 1, 2, 3. 1 plus 3 is 4. Not very well written. But we can't do that with I. What do we mean by go to the number line and move through the square root of -1? So although we use this symbol plus, it doesn't actually have the normal meaning for the word plus. So we need to sort out some rules to be able to deal with complex numbers. The rules that we have are very much like the normal rules of algebra that you've seen for many years. Firstly, if I want to look at the square root of -16, I think of the square root of 16 times the square root of -1, which is 4 times I. Very, very similar to the square root of 8 is the square root of 4 times 2, which is 2 root 2. Secondly, let's look at addition. If I want to add two complex numbers, then I take a plus bi and add c plus di. I get a plus c plus b plus di, just as if you were adding a plus bx and c plus dx. Whoops, I got the I in the wrong place there. So there we are, b plus d times I. Subtraction is very similar. If I take a plus bi and subtract c plus di, if we think of the same sort of idea, then this is written as a minus c plus b minus d times I. There's no reason at all why this has to be true. It's just that if we define everything like this, we end up with a set of complex numbers and a set of rules which make them very useful indeed later on. Let's have a look at multiplication. Multiplication, well, let's make up a rule for multiplication, which is very like our ordinary rules. A plus bi multiplied by c plus di. Well, how would you multiply a plus bx and c plus dx? You would do a times c, and if we take the last pair, bi times di plus bi times di is b di squared, plus, then if we take the outside pair, we get a di, and the inside pair, we get b ci, which is ac minus bd, because I squared is -1, plus ad plus bci. So those are all very simple and very much like using I instead of x. And then whenever we get I squared, we just write -1. So those are the rules that we've made up so far. Division is just a little bit more interesting. So let's have a little look at division. I think this is best done by looking at an example. So let's look at 3 plus 4i divided by 1 plus 2i. You did when you had to rationalize the denominator when you were doing the IGCSE. You might have had something like 2 plus 5 root 2 divided by 3 minus 2 root 2. In order to rationalize the denominator, you multiplied top and bottom by 3 plus 2 root 2 all over 3 plus 2 root 2. And on the top, that gives us 6 plus 15 root 2 plus 4 root 2 plus 10 times root 2 squared. So that is all over 3 squared, which is 9, minus 2 root 2 squared, which is 8. And that gives us 26 plus 19 root 2 all over 1. Well, that works simply because when you multiply the two numbers on the bottom, you are using a minus b times a plus b, and you basically square the square root. Well, we're going to play the same trick up here because this is just the square root of minus 1. So if we want to get rid of that idea on the bottom, if we multiply by 1 minus 2i, then we should be able to do exactly the same as we did just down here. So let's just take this little lot and get rid of it. And let's multiply top and bottom by 1 minus 2i. 3 plus 4i divided by 1 plus 2i times 1 minus 2i over 1 minus 2i. That is equal to 3. And then if we do 4i times minus 2i, we get plus 8. And then 4i times 1 is 4i, minus 2i times 3 is minus 6i, is minus 2i. 1 squared minus 2i squared. We've got 11 minus 2i on the top. And on the bottom, 2i squared is minus 4. So we have 5 on the bottom, over 5 over 5. All right, so that's dealt with division. In general, we would say that if we want to divide c plus di divided by a plus bi, then we multiply top and bottom by a minus bi, and that gives us on the top ac minus bdi squared. I squared is minus 1, so that gives us plus bd, and that is going to be over a squared minus bi squared, so that is a squared plus b squared. I squared is minus 1, so minus b squared I squared is plus b squared. Then multiplying the other bit out, we get plus ad minus bc times I, that's a c, supposed to be, all over a squared plus b squared. All right, now we've seen this number a minus bi, and this has one or two more uses than just in division. And we define the complex conjugate. So if z is equal to a plus bi, the complex conjugate of z is z star equals a minus bi. Not very earth-shattering, but it has its uses. So there is your conjugate. Notice two things. Notice first of all that if we take z plus z star, that is equal to a plus bi plus a minus bi, and that is equal to a plus a, which is real. And also notice that z times z star is a plus bi times a minus bi. This is the result we've already used. That is a squared minus bi squared. I squared is minus 1, so that is a squared plus b squared, and that is also a real number. And let's look now at the complex roots of a quadratic equation. Now, some quadratic equations have real roots, but if b squared minus 4ac is less than 0, then we have something which has complex roots, or does not have real roots. Let's look at x squared plus 4x plus 13 equals 0. b squared is 4 squared, which is 16. 4ac is 4 times 13 times 1 is 52. b squared is less than 4ac, so this definitely has no real roots. Rather than use the formula, I think it's more elegant to complete the square. X squared plus 4x plus 4 is a perfect square. To make 13, we have to add 9. So if we write equals minus 9, we now have the same equation. This side, the whole purpose of doing it is x plus 2 squared, and this side is minus 9. Take the square root, you get x plus 2 is plus 3i or minus 3i. Square root of 9 is 3, plus or minus, and the square root of minus 1 is I. This gives us that the roots of our equation are 2 minus 2 plus 3i or minus 2 minus 3i. Notice that these two roots form a complex conjugate pair. And this will always be true for any quadratic equation in which the coefficients are all real, that if it has no real solutions, the two complex solutions will form a complex conjugate pair. You can find all of this in book FP1 on pages 1 to 10.